So now that we've had a chance to talk about the different types of completion stage methods, the ones that are triggered when a single stage completes, the one that's triggered when two completion stage methods earlier finish, and ones that are triggered when either of two completion stages finish. Now let's go ahead and take a look at how you can apply completion stage methods in practice to do interesting things. And as before, we're going to demonstrate these features in the context of our big fraction multiplication and division class. So we have this big fraction package, and you can get all the code here in my EX8 folder. So the particular method we're going to look at here is part of the EX8 example, and it's called test fraction multiplications 1. And the name indicates the fact that there's also a test fraction multiplications 2 method, and that does other things, which we're not going to talk about right now. But if you look at the code, you can see it's very heavily commented. So there's other examples of doing this kind of computation in the case study example. So let's take a look and see what test fraction multiplications 1 does. So what it's going to do is it's going to actually combine Java streams, in this case a sequential stream, of course, together with completable futures. And what it's going to do first, it's going to use the generate method from the stream interface. And what generate does is it's going to call a factor method called make big fraction. And make big fraction is going to generate a bounded number of large, random, and unreduced fractions. Now, actually, I should be more specific. Generate will generate an infinite number of large, random, and unreduced fractions. And then we're going to use the limit intermediate operation to limit the number of random, large, unreduced big fractions that are generated by generate. Hopefully that helps to make sense. So we're generating a bunch of these large, random, and unreduced big fractions. Let's take a look at the make big fraction method. It's kind of a fun method to demonstrate how to use random number generators, among other things. And what we're going to do here is we're going to make a large and random big fraction. And we get the randomness by using a random number generator. And then we decide whether we make something reduced or not by the second parameter we pass to the make big fraction factory method. You can see here we're going to create a numerator, which is a random number that's uniformly distributed over the range 0 to 2 to the 150,000th minus 1. So I think you'll agree with me that's a really, really, really potentially large number. It can be absolutely gargantuan in terms of its precision, which of course is going to take a while to run, which is why we want to be able to do this asynchronously. We then go ahead and create a denominator, which is the numerator divided by a random number between the range of 1 to 10. So this will be smaller, of course, than the numerator. And then the last thing we do is we return a big fraction that will have the numerator and denominator, and then we can also indicate whether we want it to be reduced or not. In this particular context, we're not going to reduce it because reducing such a gigantic big fraction would take a while, so we don't want that to take place in the main thread of control. We want that to take place in a background thread. Okay, so just imagine for sake of discussion that we now have a stream of up to S max fraction random unreduced big fractions that are very large. And let's assume for sake of argument that S max fractions is, I don't know, 100 or 1,000 or something like that. What we're now going to do is we're going to use the map intermediate operation, which hopefully you remember from our sequential streams lessons, in order to reduce and multiply all these big fractions asynchronously in the common fork join pool. So we're going to do all these computations in parallel, or up to as many as we can run at a time in parallel using the common fork join pool. And to do that, we're going to have a method, or actually it's a local variable called reduce and multiply fraction. It's a local variable that's going to be a lambda. So here's the lambda function that we're going to be using here. It's called reduce and multiply fraction. So of course, it's going to be doing this all asynchronously. And so let's take a look at and see how that actually gets performed. And we'll look at a couple of different variants. This should also help you with some of the programming assignment number 3 decisions, because you'll see how you can use different variants to accomplish this task. So the purpose of this lambda function is to asynchronously reduce and then multiply these gigantic random big fractions. So the first thing we're going to do is we're going to use the supply async method, and we're going to asynchronously reduce a big fraction. So as you can see here, we're going to say big fraction reduce, and we're going to pass in the unreduced fraction, which is what's passed here as the parameter. So that's what we get from the make big fraction factory method. And we'll have a stream of these guys. So this reduction will take place in the background in a thread from the common fork join pool. And then after the reduction occurs, after we've got a reduced big fraction, we're then going to go ahead and asynchronously multiply that reduced fraction by some big fraction constant. So we have another constant called S big fraction, which is set somewhere else in the program. Don't have to worry about that right now. And that's going to go ahead and actually do the reduction. I'm sorry, the multiplication on the reduced fraction. And this will also take place asynchronously. And we get this to take place asynchronously by using the CompletableFutures supply async factory method to perform this multiplication in a thread in the common fork join pool. And to keep this thing from being nested, we're going to use then compose to wrap the call to CompletableFutures supply async. It's a bit of a mouthful, but that's kind of the technique you can use for then compose. So you end up with a completable future to a big fraction as the result, as opposed to a completable future to a completable future to a big fraction as the result. So you can basically think of then compose as acting like flat map to ensure there's only one level of completable future nesting. So a good thing to remember, that's the main difference between then compose and then apply. You get de-nested completable future results. Now, it's also perfectly plausible to use then apply async here instead. So instead of doing this call where we've got a nesting to CompletableFutures supply async after previously calling CompletableFutures supply async, so as opposed to having to call that twice, instead we can use then apply async. And that will go ahead and perform the multiplication on the reduced fraction in some thread in the common fork join pool. So this is actually my preferred way of doing things. I think this is cleaner code than this code. This code works, and it's a good idiom to be aware of, but given a choice, I would prefer to use then apply async, because I still end up with de-nested results, but the computation is going to run in a thread in the common fork join pool. So this should also, if you look at your programming assignment number 3, there's a couple places where this kind of technique pays off quite nicely in order to do things asynchronously, but avoid having to do nested calls to CompletableFutures supply async. So what we end up with as a result of all this is we're going to have a stream of CompletableFutures that correspond to asynchronously operating processing on the stream of big fractions that are large, random, and initially unreduced. So we're reducing them and multiplying them asynchronously as part of the reduce and multiply fraction local variable, which is a lambda function. And map is then just making sure that this lambda function is called on every one of those large, unreduced, random big fractions. Okay, so far so good. So we have a stream of CompletableFutures to asynchronously operating code. So what are we going to do now? Well, what we're going to do now is we need to find a way to collect all of these things together. And what we want to end up with when we're all done with calling collect is a single completable future that will represent all the asynchronously running completable futures that are in the background doing reductions and multiplications of these large, random, unreduced big fractions. And doing this is basically a sort of a mega join, if you will. It's kind of like the collect operation as always, but it's working on asynchronous computations. And so what the collect method is going to do, it's going to work in conjunction with a custom collector that we're going to write, and we'll talk about shortly, called the futures collector. And the futures collector is going to end up creating a single completable future that when it is triggered will contain a list of the results of all the asynchronous completable futures that we're running in the background, doing the reduction and multiplication operations. So we get back a single completable future that will ultimately yield a list of big fractions that have, at that point, when it's triggered, been reduced and multiplied. And that's the final result we're going to get. And then what we're going to do, as you'll see shortly, is we're going to go ahead and accept that and then sort and print the list. So then accept is called as the final stage here, and it's going to be passing in a method reference to a method called sort and print list, which, as the name implies, will sort and print the results when all of the asynchronous computations complete. Now, this code is just so absolutely cool. It's kind of amazing. It's really remarkable how powerful the combination of sequential streams and completable futures can be. And you'll see that that's such a powerful combination that later Java reactive streams kind of put those two things together into yet another asynchronous parallel computing model called reactive streams. And we'll see how that can be used in a later part of the course. So here's the sort and print list method. This is what gets passed to then accept here as the final stage of all these things. So sort and print list is going to take a list of big fractions, which at that point will have been reduced and multiplied. And it's going to use that clever trick we talked about before with accept either to go ahead and sort that list in parallel using two different sorting algorithms. So let's go ahead and take a look. Here you can see that we do quick sort on the list and we do merge sort on the list. Both of those things run in the background by using the supply async factor method. And then we go ahead and use the accept either method. In this case, I pass in quick sort future first, and then I pass in merge sort future as the first parameter. I could switch those around, no problem. And accept either, as we just saw, will select whichever result finishes first and then use that to print the results. Now, interesting issue is if the future has completed right away, then the action, which in this case is going to print the results, will run in the thread that registered the action. So that's one way you get the results. Otherwise, if it takes a while for either of those completable futures to finish, then the action will run in the thread in which the previous stage ran. So it can either be the calling thread or some background thread where this computation gets run. Irrespective of either of those things, the accept either method does not cancel the second future, completable future, while the first one is still running, or I'm sorry, after the first one completes. So after the first completable future finishes, whichever one it is, then the second one is allowed to continue its processing, even though this particular use case will not apply the result in any way, shape, or form. So it's important to recognize that that's the semantics of how these things work. So that's the end of our discussion of applying completion stage methods. And there's still some important stuff left over. So hopefully we'll have enough time to cover the use of the completable, the futures collector, which is really cool. And it gives us a chance to talk about yet another type of method here.